We are UPC Space Program. Welcome to our facilities at Universitat Polytechnical de Catalonia. This year, we are proud to present our new rover, CERES.
The GRASS mission of the UPC Space Program team is made up of around 35 students, divided into 7 key departments that make the development of the rover possible. The science department is in charge of formulating the hypothesis and studying the Mars terrain. The frame department designs a chassis that connects all subsystems, providing a solid yet lightweight structure for the entire rover. The brass department develops a 5 degree of freedom robotic arm capable of manipulating objects and collecting samples from the Martian surface. The traction department is responsible for the rover's mobility system, including wheel design, suspension and propulsion to adapt to Martian terrain. The control department develops the software that allows the operators to control the rover and ensures the proper operation of all onboard systems. The Grasshopper team is responsible for the development of an autonomous drone with object and surface recognition capabilities. The marketing and business departments promote the project professionally and through social media platforms. The logistics and treasury departments ensures the correct economic and event management. And to coordinate all this dedicated team, we count on our mission leaders, and we are all working towards the same goal:
To participate in the European Rover Challenge. At UPC Space Program, we're building more than just a rover. We're building a community. We work as a real-world engineering team where we, the students, are involved and lead every stage of the development, from the very first sketch to a mission-ready rover. And our impact doesn't just stop at the workshop. We're deeply committed to our community, as we use your projects to inspire future generations in classrooms and beyond.
For us, the European Rover Challenge is the ultimate proving ground for our technology. That's why it's such a key element for our project. It's a high-pressure arena where we validate our work on international scale, while competing against the best engineering teams and simulating a mission to Mars.
As humanity advances towards multi-planetary colonization, securing in-situ water resources is a critical mission priority. To meet this challenge, our rover is engineered to locate subsurface ice by performing advanced terrain conductivity analysis via electromagnetic induction.
You've just seen our brand new rover, which with an optimized frame and science design, which is going to allow us to prove our hypothesis better. Let's head now to our team that's going to show you all of its components.
The control department is responsible for developing the software architecture and integrating the hardware required for the rover's operation, such as onboard computers, microcontrollers, cameras, and communication system. The main software architecture has 3 modules: the graphical user interface, used to control and monitor the rover, the main software, which is built using the ROS2 framework, and finally, the firmware that is run on the microcontrollers. The rover is also equipped with a custom developed autonomy stack, which has 4 main modules: localization, path planning, trajectory control, and finally hazard detection.
The chassis is divided in the first submodules. It's our newest design, and we're working in parallel with the 2025, so we assure a continuous workflow on rover modifications. Firstly, we've got the power module that gives energy to all the rover, then the traction electronics module, the control module, that's the brain of the rover, and the robotic arm bay. Additionally, we've got the emergency button that shuts all the actuators while maintaining a communication flow.
The science department is responsible for developing and validating the mission hypothesis. The science module is divided into 3 subsystems: sensoring, sample collection, and a stereo. The sensor module includes environmental, electromagnetic induction, infrared temperature, and distance sensors used for calibration and verification.
The robotic arm is the most versatile tool the rover has to perform different tasks. It has 5 degrees of freedom and can lift up to 2.5 kilograms of weight at the tip of the gripper. The most important development we've done are the CAN chips, which are custom boards that are installed in each motor, and they are connected through a CAN bus network.
The traction system begins at the control module, where our custom PCBs receive the motion set points and set them to the motor driver. The driver controls the 2 degrees of freedom of each wheel, propulsion, which moves the rover forward and backward, and steering, which defines the orientation. Both axes are controlled in closed loop, comparing the desired movement with the real response of the rover. We also have a homing system that allows us to move the wheels to a reference position in a reset. Mechanically, the traction system is divided into independent and interchangeable modules. This allows us to replace damaged parts during testing or competition.
The design and development of our newest drone has been accomplished by Atlas, our specialised droning team. We are proud to present the Grasshopper. The Grasshopper's drone is designed to be an advanced test bench to integrate different innovative technologies such as optimal sensors and onboard image processing, a modular high-energy density battery management system, RTK GNSS, high-speed radios, amongst other innovations. For environmental awareness and autonomous navigation, it uses various digital cameras, optical flow sensors, and LiDAR. These sensors provide essential data for autonomous navigation with the help of a high computing power of a Raspberry Pi 5, which communicates with the autopilot in the main flight controller to manage the drone's movements. We're also working on integrating safety features such as an electronic circuit that automatically triggers an auto landing sequence in case of communication loss and shunt plug that allows for manual power shutdown if needed. Our control department has already tested autonomous systems using Gazebo and other computer-aided simulations. For machine learning, our drone can identify various colours and shape probes and accurately position itself using Arvico markers and image processing techniques. The drill module is capable of extracting subsurface samples from depths of up to 30 centimetres and measuring their mass. In addition, a 3D printed container attached to a load cell allows the system to store and weigh both the rock and regolith samples collected by the robotic arm, ensuring precise and efficient sample retrieval. In the event that liquid is detected, the rover is equipped with a pH sensor mounted on the robotic arm to analyse the sample directly on site. Additionally, the rover includes a liquid pump system connected to a tube also integrated into the robotic arm, allowing part of the liquid sample to be transferred safely into a sealed onboard container. This system enables secure sample storage and transport for further analysis. Depending on the mission requirements, the robotic arm can be equipped with 3 different end effectors. One, designed for collecting ground samples such as rocks and regolith, another for measuring pH levels and collecting liquid samples, and a third, specifically developed to operate human-made control panels, including switches and plugs. The robotic arm integrates a stereo camera, providing the operator with precise visual feedback for safe and accurate manipulation. This camera also allows the rover to analyse its surroundings in real time, enabling object detection and autonomous functionalities.